three experiments like Trish introduced. The first one's on vacuum chambers, a lot of fun stuff. What happens when you put stuff in a vacuum? And then on blast shields, that's like basically space armor or armor for spaceships and stuff. So when like a piece of debris or a little micrometeor hits a spaceship, it doesn't destroy it. It can shield against that. And the last one is on Shockwave Schlierens is what they're called. It's kind of, looking at the actual shockwave. It's really cool because a lot of slow motion stuff. And so without further ado, I suppose we will start. I'll share my screen, and then what we'll do is between video, if you guys have any questions, let me know and I'll answer your questions as best as I can. So let's get going with make sure. Whoops, there we go. Okay. Cool. So vacuum chambers.
Welcome, boys and girls, to the New Mexico Institute of Mining and Technology. My name is Jason.
I'm Gabriel, and we are with the mechanical.
Can everyone hear?
Department.
Today we got a little experiment to show all of you. We're going to be putting an assortment of items into this pressure vessel to show you what happens when they go under low pressure.
Yeah, so we got a bunch of things to test under vacuum. We got water, because water supposedly boils at under vacuum, and then we have bubble wrap because it's full of air, so I don't know, probably popping stuff. That'll be cool. Then we have a glow stick because we have no idea what's going to happen if you stick a glow stick in there. Is it going to explode or get brighter? I don't know. We'll figure it out. And then the last one is slime. That's going to be pretty interesting. So you can join us, and we will go on the experiments here shortly. Okay, so like we were talking about, our first experiment is going to be the water. We should see it boil under a vacuum because the vacuum decreases the amount of temperature you need to boil water. So we put that in our chamber, which is this guy right here, this big steel container. It has this rubber gasket here, so it keeps air out. When we put our lid on, you should be able to see that. Give it a couple taps around the edge, help it seal. And then over here we have our vacuum pump, so that's going to give us a vacuum in our chamber. I'll turn this guy on. Oh, it works. So back at the chamber, we should be seeing that the vacuum is increasing with this dial, but it's not. So, we gotta close this valve. That's the outside air valve. There's the valve for the vacuum, and it's working. So we'll let that go, and we'll check back when it's started.
So to explain to all of you what a vacuum is, if you're not familiar, is what we're doing is we're sucking all the air out of that, that space in there, and it makes things do weird stuff. So like the water will boil even though it's not, because there's no air. It doesn't need, it means that the temperature, you don't need a high temperature to boil water if you have no, air pressure or anything like that. It's really, really interesting.
So I don't know if you all can see it, but we're starting to get bubbles forming on the water cup, along the edges, and all kind of like when you've got your pot of water on the stove. So we'll keep it going and okay, so as you can see, we're getting the water to start to boil. We're kind of at the top end of what our vacuum can do, or our vacuum pump can do, but I'll keep it running and we can see it go a bit more. Maybe it'll go more. Okay, so that looks like all the bubbles we could get out of that water. So that's pretty cool. So I guess we'll see what happens when we let all the air back in the chamber. 3, 2, 1. Okay, so for this one, we're going to try the slime. This should be pretty interesting, so I guess let's see. Got a bunch of glitter. I'm going to throw this in. Oops. Okay. Okay, so let's see. That's some pretty cool stuff.
So I see people are having a hard time hearing. Is it better now? I turned up my volume as much as it could go.
Yes.
Okay, I'll keep going then.
Here we'll get our chamber ready. And for this one, we'll take this out so we don't get that dirty, and we'll see what happens. That's pretty funny. Okay. So lid. Get it going. Close off the outside air. And turn on our vacuum. So, I think it's time to open it up. Are you ready to open it up?
All right, so next up, we are going to try these splat pigs, and also some marshmallows, and see what happens when they go into the device. All right. So what we're going to do is we're going to put our little piggies in here. First little piggy went to market. Second little piggy went home. Third little piggy had roast beef. And fourth little piggy is going to get blown up by a vacuum. So we'll just put our lid back on, close our valve, start up our pump.
Oh, that Trish got a good. Oh, you guys are having a hard time seeing it?
So as you can see, the pigs have now, or at least the gold one, has filled up almost the entirety of the container. The air inside the pig, the pressure was much higher than the air outside. So that air is pushing outwards and expanding the pig, and since the pig is super stretchy, it just stretches ultra wide. Another reason is the pig is actually filled with water. The way they make it is it's filled with water. And that water, as we showed in our previous one, started to boil, which created a lot of steam. It created a bunch of steam, which then fills up the pig even more and creates it too, and makes it blow up even bigger. So what I'm going to do is I'm going to release it. We should see our little friend shrink back down to size. We will open this up. We can see our little friend. You see our
Let's see if I can get it. That started lagging on my end too. So let's try that.
little friend is back to normal. He's a little stretched out a bit than he was before, but still just as good.
Okay, for our final experiment, I'm going to be showing what happens to our marshmallows when we stick them in the vacuum chamber. You can see we have some pretty cool faces, so you can kind of see how they look before and after. So we'll set these guys in here, kind of face up. We'll see. Whoop. Give them some space. Put on our lid. Whoop. Lid. And then turn on our vacuum. And goes this. So this whole process takes about 15 minutes to suck all the air out of the chamber. Not even all the air, you know, just the air out. It was interesting, if you look there, we didn't notice this until looking at the video, is the marshmallows actually kept expanding up until, I guess, something broke and it let all out, so they stopped expanding. So it's kind of interesting to see there in the review. Let's see if anything happened, because it didn't really happen. Oh, they kind of shrunk. That's pretty cool. Let's see what happens when we pull them out. There we go. Man, they look like wrinkled napkins. Let's see. Here's an original one, and you can see good chunk of the air has been sucked out of them. This almost getting bigger, it looks like, again, but mostly shriveled. This guy's even smaller. He's not too happy.
Welcome, boys and girls, to the New Mexico Institute of Mining and Technology.
Well, that's the end of that bit of video. So, and I saw a couple of you saying, you know, high pitch, and to explain that we sped up the video. That way you don't have to sit there for the 15 minutes, you know, the air gets sucked out of the chamber, because it's kind of boring when you just sit there staring at it. I know so we sped it up in the video. So if anyone has any questions about it, let me know. You know, it's really weird what things do when you take all the air, like that slime stuff. You know, we kind of molded it around and got a lot of air. It got in there. So when we turned on the vacuum to pull all the air out of the chamber, it tries pulling the air out of the slime, but the air is kind of trapped in it, so it kind of just expands into a big old blob. And then once you let all the chamber, it kind of smushes back down into its, you know, a little smaller thing than it was. Same with the marshmallows. They kind of, you know, shriveled up real bad because we sucked all the air out and then put it all back in, so it back down. So, oh, Trish, you're muted.
How long did that take in real time?
Yeah, in real time, for one thing, it takes about 15 minutes. 15 minutes to suck the air out. So, it takes a little while. That's why we fast forward. Yeah, expanding is interesting. So that happens when, for the little pigs, I wish I had one with me, but when you have those have their own bit of air in them, right? So when you take all the air out from around the pig, the air in the pig wants to push it out because it's not balanced. Now, you know, the air outside, there's less of it there and there's more in the pig. So it wants to expand because it fills up it wants to fill up the space. So that's why all those things expand. Yeah. Things that, you know, like the marshmallow, it expanded, but then, you know, it finally broke. So it stopped expanding. So when the air came back into the chamber, it collapsed because, you know, expanding broke the marshmallow's structure. It made it, you know, not be able to stand up to normal pressure after that.
So there's a question too about they were wondering, Ryan is wondering if a Lego brick could be put in the vacuum.
Yeah, we could put a Lego brick. It probably wouldn't do anything because I don't think it has air in it. So it wouldn't really look cool. And Lego bricks are strong. I mean, we all know that. You step on one, it's not going to break. Your foot's going to break. So do much under a vacuum.
This is Miss Rodriguez in Rio Rancho. My class wants to know, with the marshmallows that are all shriveled up now, what would happen to them if we just sat them in a regular room for a while? What would happen over time?
In a regular room, you know, without a vacuum or anything?
Yes, after, like in the state that they're in right now.
Oh, in the state. So, you know, after pulling them out of the chamber.
Yes.
So I don't think it would be much different than them getting stale, because I actually took a bite of one after. It was gross because it wasn't fluffy anymore, you know? The air pockets in the marshmallow make it fluffy. So once we sucked all the air out of it and then it lapsed, there were hardly any air pockets. So I took a bite and it's like chewing on a hard piece of Jello sugar. It was gross.
Thank you.
You're welcome. Well, any other questions? If not, the next video is...
Yeah.
Go for it.
I'm Joaquin Raff. Does it work the same as like a dehydrator?
So not quite. So dehydrators suck the water out of the air. So similar, because I suppose there's water in the air we're sucking out of the chamber, but you know, a vacuum chamber, it sucks out as much air as it could. So there's just physically no air in there. So if you put like a candle in there, you know, it needs oxygen to burn. It won't have oxygen, so it won't burn because you out that space. Dehydrator, you suck the water out. So, you know, you can dry stuff out, make beef jerky.
I have a question in the chat. How can kids make their own vacuum?
So there's some cool YouTube videos on that. It's actually not that hard. Basically, like you saw, I'll pull it up again and I'll pause it so you can see.
Welcome,
So
boys and
really
girls,
it's
to
just
the
a
Next
pot,
Intelligence
right? I
Institute.
don't know if you can see my mouse or not, but a pot, something strong. Then you have like a gasket, a chunk of rubber so air doesn't leak in. And then you have a lid, and our lid is clear. You can also use a clear container of some. And then the vacuum. The vacuum is the main thing. It's a vacuum pump. It basically just pumps air out of the chamber, kind of like when you use a pump to fill your tire. It just does the opposite. Instead of filling, it sucks. So you can find stuff for that on YouTube. It's a cool little project.
Another question. Let's see. Can a stuffed animal be in the vac? Maybe. is the question. And then would a plastic bag shrink in the vacuum?
So stuffed animal. I don't know what a stuffed animal would do. That's something that we might have to try. I suspect it wouldn't do too much. It might shrivel a little bit because it might suck all the air out, which all the fluffy stuff in there just gets, maybe smaller. Instead of holding air, it gets smaller, so it might shrink. Put a stuffed animal. A plastic bag, it depends if it's filled with air. If it's a lot of things filled with air expand. When you suck the air out, it's to push itself out now that there's less air around it. So I think the plastic bag would probably expand if it's full of air. If not, I don't think it would do. A ball, what would happen if a ball was in there? Same thing, if it's full of air, it would probably puff up, unless it was a really thick wall ball and it could, because if the stronger the thing is, the less it'll expand, right? So like slime is not very strong. You can tear that apart in your hand. Whereas the Lego example from earlier, Legos are real hard. They're a Lego by hand easily. So that wouldn't do much. Balloons, like those pigs you saw where they expand because they're full of air. Oh, there you go. Basically just like that. Well, if that's about it, we'll go on to the next one, because the next one's my favorite video actually, because it's got explosions and stuff. It's a lot of fun. So hopefully it doesn't, or hopefully the internet's good, because don't want to miss the explosion. Whoop. Can everyone see this all right?
Yeah, it looks like it.
Welcome everyone to the second section, our second experiment from the New Mexico Tech Mechanical Engineering Department. What we're going to be doing today is building a blast shield. For those of you who don't know, a blast shield is basically exactly what it sounds like. Spacecraft, for example, use them to stop orbital material, to stop space debris from, destroying the spacecraft. It stops all that debris from, penetrating the spacecraft. So I'm making an example of that blast shield, and you'll see a little bit later how the example is tested with an actual explosion up at EMRTC. So without further ado, we'll get into it. So as you can see, we got a handful of materials here. Right here we got some steel plates, both steel plates, about 1/8 inch thick. That should be a good face layer. And then we have our aluminum honeycomb. That's going to be a spacer between the two layers. And you'll see this all when we go to put it together, but it's going to look something like that. And then within the inside, we are going to put some Flex Seal, some rubbery stuff, and some foam, so we can kind of see what happens if it makes a difference with the two different materials, or two different, rubber versus foam on the inside, holding everything together. In the end, it should look something like this. Not too thick, not terribly heavy, but let's get to it.
The project that we're sharing the videos from was funded by the New Mexico Space Grant Consortium, and our objective was to expose freshman engineering students in the mechanical engineering department at New Mexico Tech to solving some real-world NASA space problems. The specific problem that is addressed in this video is designing a shield to protect a spacecraft or satellite from impact from micrometeorites. Micrometeorites are small rocks or pebbles traveling extremely fast that could impact a spacecraft and cause damage. So the students were tasked with designing a shield of some sort to protect some sort of sensitive equipment from that level of impact. Part of this project, the students are given wide freedom to select a wide range of materials to design their shields out of. I've seen everything from phone books to paper, styrofoam insulation, fiberglass insulation, steel, aluminum, wood, polymer solutions, honeycomb solutions, a wide range of materials and combination of those materials, right? Maybe the solutions that succeed were overkill. Maybe the solutions that failed did have some beneficial aspects to what they did, and in some ways they succeeded. So learning from our failures is a great thing in engineering in order to push us to a better solution in the long run. So in addition to be given wide latitude in what they choose to design their structure out of, we provide the students with access to the freshman design lab in the mechanical engineering building at Tech. They also have access to a number of graduate and undergraduate teaching assistants to help them along with the project. This lab is the same lab that they'll use for their robotics project at the end of the semester, where they look at coding in Arduino, wiring their circuits and robots, and testing them out in a competitive environment to see whose performs the best. So both the blast shield project and the robotics project are team efforts. So this provides them a place to come together and work as a team to solve their problems, bounce solutions off each other, and come up with the best options. Now, we can't really expose them to real micrometeorites in outer space, so the next best thing that we had was to use the EMRTC explosives testing range that's on campus, part of the research arm of the university, and use explosives to accelerate hex nuts to not quite the same speed as micrometeorites, but a very high rate of speed, and then look at the impacts that are caused.
We have our first layer of steel, 1/8 inch of steel plate, and then we have our aluminum honeycomb here, and then our back face of steel. So the idea being here, when we have a projectile of some sort, whether space debris or whatever it will be, when it comes and hits the face plate of steel, the plate of steel, it won't stop, it'll break it apart though, and that broken up projectile will be traveling in this space, and hopefully the small stuff will be caught in the rubber and the foam, and anything bigger than that, anything that still has energy, will then be caught by the back layer of steel, because it shouldn't have enough energy to go through that. So anything that comes from this side should not go out that side. So it should be a pretty decent blast shield.
Now that the students have finished building their blast shield, we're going to go out to EMRTC, the Energetic Materials Research and Testing Center at New Mexico Tech, and set off an explosive charge it will accelerate pieces of metal into the shield. So the pieces of metal are going to simulate the micrometeorites, and then we're going to use some high-speed imaging to track the explosions pattern and follow the objects until they impact all of the shields. In this setup, the explosives charge is placed in the center, and then the student projects are placed all the way around the outside. The students that choose to are accompanying us out to the site, and we have a bunker on the top of the mountain where they will watch indirectly the explosion as it happens. So we also get to experience Doppler effect. We're far enough away because we need to be safe, that you can see what happens before you hear it in the class.
Again, it contains 3.2 pounds of C4. Everybody have it? 5, 4, 3, 2, 1.
Hear it? You'll have to come to Tech and be a student if you want to get to do the project for real.
So that was the blast shield project. I've got another student from Tech here as well. I'll introduce Jason. He should be hopping on. So we'll, if you have any questions, now's a good time. Otherwise, I'm going to keep playing this video of the actual explosions, because that's the cool part. And it's cool because you can see stuff going straight through, like that one right here, you can kind of see stuff going straight, really doing a good job as a shield. But like on one over, oh man, over here, that one looks like it's doing pretty well kind of around the edges. Can't really tell from there. You have to look at it after if it stopped all those things or not from going through it. Oh, Jake, have you?
I'm here.
So yeah, as they said, 3.5 explosive. So it's really cool to, you know, be able to see if your, you know, your the shield you made will work. You know, if it's really hard actually to stop things when they're moving fast. The faster something moves, the harder it is to you know, shield from it, because it'll just go straight whatever shield you make. You know, just plow through. So how long does it take to make a shield? So we made ours in about 10 minutes, 15 minutes. It worked mostly well from the experiment. Where what was interesting is the chunks of metal, they stopped in the part that had the rubber, but not on the parts that had the foam. So that's kind of weird. So the rubber must have done a really good job at slowing them down, because I guess, you know, you like throwing a ball at a soft wall, it'll slow it down over time.
And the builds do vary in time. Some of them are a little more complicated than others. The one that was shown to you was a little more simple of a build. But there are definitely some that got really creative, really interesting, but some of them took a good couple of weeks to finish.
Yeah, so what this kind of shows is like spaceships, I wouldn't have thought originally, but turns out, you know, all the little tiny particles, you know, that orbit the air, the different trash in space and the little meteoroids, those things are traveling, even though they're super small, so fast that if it hits something, it'll just punch straight, you know, straight through it if you don't have a shield. So it's really important for spaceships to have a good shield of some kind. So if there aren't any more questions, we'll head on over to our last video on Shockwave Schlierens. That's what it's called. You know, you can kind of see the shockwave here, this hole, where the air looks kind of weird, like it's traveling out. That's a shockwave. Anthony, I saw you raise your hand. Go ahead.
And a blast shield for a rocket is almost like a normal shield, or better?
So it is just a normal shield, but you know, you make it special because the things you're trying to stop are going so fast. You have to make it just for those. So you know, there's different kinds of shield. If you're trying to protect against something that's going slower, then you don't need as strong of stuff, right? And if you're trying to protect against something that's going super fast, like, you know, all the metal from the explosion that's get flung out, then you need something a bit more heavy duty.
Thanks.
You're welcome. So we'll head on to the next one. Which shield is stronger? Jason, do you remember which shield was the best?
So we had a couple different ones. The one that we showed you being built did actually a really good job as a more of a catch box because it went through the first layer of metal but not in through the second layer. So a lot of the shrapnel that went into it was actually caught within the metal itself. We had another group that did a really good job that built almost a pyramid shape of metal, and they welded these pieces of metal together, and almost I don't think anything actually was able to penetrate that. So I'd say probably that one did the best job, at least as a shield itself and not as a catch box. Catch box, you want to actually catch all the little bits of metal that's flying at it, while a shield, you want to actually just full on deflect it and don't let it get anywhere into the ship itself if you're building this for a spaceship.
I like that slow motion. That's real cool. Okay, well, anything else? Or any other questions?
Doesn't look like it.
Okay, we'll head on to the next one. The next one's, you'll be able to see the little explosion in even slower motion, so that's really cool. And Dr. Hargather, he's a professor here at New Mexico Tech. You'll see if I...
An associate professor of mechanical. My name is Dr. Mike. I am an associate professor of mechanical engineering here at New Mexico Tech, and I teach classes in fluid dynamics, thermodynamics, and I do research on explosives. This is a Z-type Schlieren system where we use it to look at density differences in the air. And the system starts here with a light source. We use a simple LED, and that LED is located at the focal point of this mirror. So the light comes out from the LED to the mirror, reflects off the mirror now as collimated light, and comes all the way back through what we define as our test section, and then off of this other mirror that's here that directs the light back towards the camera. And so this whole system of the path that the light follows makes a Z. And that's what we call it, a Z-type Schlieren system. Right in front of the camera, what we have is a razor blade. And so this razor blade is what actually gives us the Schlieren effect, because it causes light rays that are bent anywhere in this system to interact with this razor blade differently. What we have right now is we have a simple candle here. And if we look on the monitor, what we can see is we can see this light-dark variation of the grayscale intensity. The work that we do is really to understand the fluid dynamics of explosion processes. And that includes the shock propagation, that includes how shock waves move and interact with objects. And
Here, let me pause it for a second, see if we can get some of the lagging off. Oh yeah, internet's not too happy. So.
And it's also about the fluid dynamics of those gas processes with how they expand. So this is a lot of work that's similar to aerospace and aerodynamics research, and a lot of these techniques are also what you would find in supersonic wind tunnel testing. So here we're using the Z-type Schlieren system because we have mirrors. And we also do this with lens-type systems, which we think of as just a straight line system with lenses. The real difference is the size of the mirrors versus lenses that you can obtain. So we're using the mirrors here because they're a little bit larger than the lenses that we have available. So we use a Schlieren system to study shock waves from explosives. And so we can use a high-speed camera to record the explosion process and then visualize the shock wave using the Schlieren system. So I have Savannah Torres, my grad student here, who's going to help us record this with the high-speed camera. Are we ready?
Yes. So here we have a Schlieren image of a simple snap pop. So you can see it's coming down into frame, and it's gonna hit the surface. And once it hits, you notice that it bounces a little bit, and then it will ignite and explode. And once it goes, you can see the shock wave that starts propagating through the field of view, and then you get all this turbulence that occurs due to the gas cloud, and then you can see all the fragmentation from the casing that it was in.
So we filmed this at 25,000 frames per second, and that really allows us to capture that shockwave propagation. When we think about a shockwave, it's moving at faster than the speed of sound. So speed of sound in air is about 340 meters per second, or about 760 miles per hour. So we really need to have a high-speed camera to be able to capture that shock motion.
I'm Savannah Torres, and I am a PhD student in the Mechanical Engineering Department, and Dr. Hargather is my advisor. I use Schlieren imaging for my PhD research, and much like we use Schlieren for gases, we can also use it for solids. So I do shockwave propagation through PMMA, or optically clear materials. So you can see through this, and much like when you're imaging shockwaves propagating through a gas, you can also see the shockwave propagating through the solid material. And so one of the goals is to look at how this PMMA fractures. I did my undergrad here at New Mexico Tech in petroleum engineering, and I had taken a class with Dr. Hargather. I took thermodynamics with him, and he gave us a brief introduction of everything that he does, and I found everything that he did very interesting. I really enjoy fluids, so that's when I decided that I wanted to do my graduate school with him. I chose to come to New Mexico Tech because of the small class sizes. You get a lot of individual attention, and there's so many hands-on opportunities that you can have. I came to a reach out, like a high school reach out day through the MESA program, because I'm from New Mexico, and I saw some of the things that they do here at Tech, and I thought that it would be awesome to come and have some hands-on experience with some of the things that they do here.
I think one of the best things about New Mexico Tech is that our students get real hands-on experience. I have multiple undergraduates that work here in my lab. They get trained on high-speed cameras. They learn how to set up these Schlieren systems, and then they get to apply it to real-world funded research. And it's not just understanding what you learn in the books, but it's learning here in the lab. It's learning doing research. It's learning doing the laboratory classes that are part of the education. And it opens doors for jobs. It opens doors for graduate school and careers afterward. My name is Dr. Michael Hargather.
There you go. Sorry if it was laggy. I guess my internet's not doing too great. Jason, would you mind sharing your screen? At least while we take questions so they can see all the explosions and stuff.
Yeah, give me one sec. Keep sharing yours so I can set this up. Do we have any questions? Let's see. Oh, Dr. Hargather's here.
Oh, welcome.
Would you like to talk about your work at all, Dr. Hargather?
I'm happy to field any questions.
So it looks like there's a question that says, what's the difference between sound waves and shock waves?
That is a great question. And the difference really is how fast the wave is moving and how strong it is. So a sound wave will propagate at what we say is the speed of sound, which is in normal air, it's about 760 miles per hour. So really, really fast. And a shock wave is a wave that travels faster than the speed of sound. So we normally talk about shock waves as they're traveling at some Mach number that's greater than 1. So they're moving faster than the speed of sound, which also makes them dangerous, that they actually carry a pressure rise across them. So we think of it with sound, if someone is talking to you, the sound doesn't really hurt you, right? And you hear the sound via those waves impacting your eardrums and causing your eardrums to vibrate, versus a shock wave that is propagating faster than the speed of sound can have a pressure jump to it that can actually be very hurtful to your ears, or even hurt your body if it's a strong enough shock wave. So think of the sound of when someone pops a balloon, how that really sharp sound, how that sounds to your ear, or when a large firework goes off, like during the 4th of July, that you can feel some of the booms when some of the big fireworks go off. That's actually, you're feeling the shock wave that was produced from the explosion of that firework as it's hitting your body. Any other questions?
There you go. Thanks, Jason, pulling that up. Hopefully it's not laggy on my, so it must have been my internet. So hopefully everyone can kind of see that a bit better.
So
We
a
do have another.
concussive,
Oh, sorry, go ahead.
a concussive force, no problem. So the question is a concussive force a sound wave? I would think of the concussive force as being more related towards a shock wave, really, because when we talk about a sound wave, we think that a sound wave really carries no force with it, versus a shock wave actually has a pressure jump associated with it that causes a force. So there's another question of, are there different types of shock waves? Really, the different things that can be a part of shock waves is really mostly just how fast they're traveling. When we look at a shock wave in general, there's really only one type of shock. We just talk about shock waves moving at different speeds, or we can have different sort of shapes of the wave. Think of it as throwing rocks into a pond. When you look at throwing a rock into a pond, you get water ripples that are going to propagate outward circularly everywhere along the surface of that pond. And that's really the same way that a sound wave or a shock wave will propagate in air. Just the difference is in air, it's propagating in the full volume of the air and not just on the surface of the pool. And really the only difference is how fast that wave is moving. So with water waves, we can think of, if you throw a larger rock in, you might create a larger wave that's going to move faster and may carry more force with it. The same thing if we say set off a larger explosion, we're going to get a faster moving shock wave that would be producing more damage. And in general, water waves, thinking about waves on the surface of water is a great analog to thinking about sound waves or shock waves. So there's a question of where we can find the recording of this. I believe New Mexico Tech, we will get these videos up on our mechanical engineering website. So we will have those up next week. And I don't know if if the formal recording is being posted elsewhere by the Science Fiesta.
Yeah, I can go ahead and take that. If you go on to the Explorer's webpage, to the Science Fiesta page where you found all the events, right at the bottom there's a YouTube link, and they're all there on the Science Fiesta YouTube. We're usually getting them up by the end of the day or the next morning after we've recorded them.
Yeah, then we'll put them on our mechanical engineering, the full videos, we'll put it on our mechanical engineering department page. That way you can hopefully see it without lag.
We should hopefully have a lot more videos upcoming soon. We are planning on getting a lot more videos so we can showcase what we do here without having people actually have to come and see it in person.
Okay. Well, any other questions about any of the general?
I think there's one other question there about student wants to know which wave is strongest. So the strongest wave would be, as far as the shock wave goes, the strongest shock wave would be the fastest moving shock wave.
Yeah, so that's kind of like our blast shield thing where, the faster something moves, the harder it is to stop, the more energy it can send out. So, main reason we wanted to show you all this. Well, I suppose we're kind of showing you what goes into mechanical engineering, some of the cool stuff. Where all this is related to engineering, so you can explain how all these different phenomena work, how come a vacuum chamber makes things shrink sometimes and get bigger other times, or why, how to build shields to protect spaceships from little meteoroids, stuff like that.
And really, we want everyone here and all the kids and everyone here to get interested in mechanical engineering. It's a great field, and science in general. Any part of the STEM is a great field, and there's so much you can do and so much you can explore. There's really is some unlimited possibilities on what you can create once you have the knowledge for it. And so really, we want people to get excited about it. We want people to keep getting interested and wanting to come into this field and hopefully come to tech. It's a great school. There's so much, available here. There's so much you can do. It's one of the few schools you get so much hands-on experience and so much you can really get into the nitty-gritty of everything.
So it looks like we have a couple more questions. I don't know if it was answered yet, but what is a shockwave? And then do all explosions have shockwaves?
So all explosions have shockwaves, and what a shockwave is a shockwave is a compression wave that's moving faster than the speed of sound. So that's its definition, is being that compression wave that moves faster than the speed of sound. And so the other defining characteristic of a shockwave is that it has a jump in pressure, an instantaneous jump in pressure. So we think of that you don't feel anything, and then when a shockwave impacts something, we see instantly that there's a pressure force applied. And it's those two things that define the shock.
Let's see, we're kind of going back to the vacuum chamber. There's a question about what would happen to a robot if it was in the vacuum chamber.
Well, that one's one of those ones you kind of got to test. I couldn't say. It depends on how you build the robot, right?
Ideally, if you build it strong enough, as if with a lot of space probes or a lot of spacecraft that go out into space, which is a vacuum, they should be perfectly fine, so long as you design it properly and you build a robot that's strong enough. They should be fine. They should be able to withstand that lack of air pressure. Really, what the things that get affected by a vacuum are things that have air in them. Things that are, have, air inside them, because that air is wanting to get out. It's wanting to fill the space that doesn't have air, where there's a vacuum. And so really, those are the things that are going to get affected by it, less so metals or anything like that would probably go into a robot.
Right, well, there's another question. Can you prevent shockwaves from hurting you?
So the best way for that, I mean, kind of like we saw in the middle video, is think about using different sort of protective shields, or you can stand behind something. Think of it again like a water wave. If you look at how water waves move and how we protect things like boats or marinas from the waves that are on the water surface, we build different structures to reflect those waves away from where we would keep boats. So the same thing for protection from a shockwave. You could think about building a wall to protect you, or have any sort of a structure that between you and the explosion would give you protection. And how strong are shockwaves? It depends on the speed. We can have very, very weak shockwaves that are actually, if you clap your hands really loud or pop a balloon, you're actually producing a very weak shockwave. And so that you can think of how that feels against your ear when you pop a balloon. And so that's a weak shockwave. And you can get stronger shockwaves with things like explosions, or even some volcanoes. There's some volcanoes that when they erupt, they actually can produce shockwaves, and those can be really strong shockwaves for large explosions. And certainly if a meteor hit the water, it would create a huge wave and sound. And a meteor, as a meteor is coming in to the atmosphere, it's normally traveling at several times the speed of sound. So it has a shock wave as a part of it because it's traveling faster than the speed of sound.
Anthony, do you want to go ahead and unmute and you can ask your question? Or do you not have a question? You have your hand raised on the thing here. Oh, you're good. Okay. Ryan, did you have a question? You had your hand raised too. Maybe, maybe not.
So I was wondering, like, for the blast shield, like, how big a shockwave can the explosion make?
That would really depend on the size of the explosion. And it's really, if you think about small explosions like the fireworks that you can throw on the ground and they'll explode, they're really weak little explosions that just kind of sound almost like a balloon popping, and all the way up to large explosions that we use for things like mining or that the military uses can be extremely strong. So there's a wide variety depending on the size of the explosion itself or the size of the explosive.
Thank you.
Great question.
You're
So
welcome.
we have another one here from Chance. It says, how big would a shockwave be if a bomb went off? Which was kind of similar to what you're talking about there, but.
Yep, it depends. It depends, like I said, on the size of the explosive material. And our state of New Mexico, really, we have some unique history and unique research on explosions that have happened here in the state. And if you go back and if you ever have a chance to go to the Nuclear Energy Museum or Nuclear Museum that is in Albuquerque, you can learn about nuclear explosions, which are some of the largest explosions that humans have ever learned how to make. And the very first of those nuclear explosions was actually performed here in New Mexico on White Sands Missile Range. So actually only about 30 miles from Socorro. So you guys, for those of you that live here in New Mexico, you really live in one of the homes of explosions. It's kind of a cool thing about our state.
So do we have any more questions? It's been great. All the questions have been really great and we've been getting good answers. So I appreciate that from you guys. Do you have any more shockwaves in water?
So yes, you can produce shockwaves in water. The tough thing with water is you have to move a lot faster. So the speed of sound in water is about 3 times the speed of sound in air. And so you have to just move a lot faster to get a shockwave in water. And certainly strong shocks can hurt people, and even relatively weak shocks can hurt people's ears. If you've ever heard a loud firework, it really can hurt your ears. That's why we're always careful with explosives.
So, at the very least, you guys learned, some ideas for if you want to ever build a spaceship, make sure it's made out of something strong so it doesn't, like in the vacuum chamber, you don't want your spaceship expanding or getting shrunk down. And you want it to be able to withstand all those meteors hitting it so it doesn't, break. So you learn anything. Mechanical engineering, that's where you build spaceships. So if that's all, I think we'll end it here.
There's one more question. It says, do you make the shields for the Army? like blast shields?
So those ones specifically were just simply a project for the school itself. However, we do actually do quite a bit of work with, we do have some government-funded programs that we do. Myself, junior and seniors had what we call junior and senior design projects, which is where we are given a task, we're given, you know, a problem that we have to solve, and we're asked to make something for it. And sometimes those problems are actually given from NASA. We've had some from the US military, we've had some from basically almost any industry that could possibly use mechanical engineering. We've had some form of funding from them to fix a problem. So while those blast shields specifically were not for that, they definitely could be used, and it's a lot of research done by the Army and NASA, and all those have done very similar research, just with often higher budgets than we have. We have done quite a bit of work on different problems for primarily the Air Force and NASA would probably be our most, the ones who would use us the most. We've worked with White Sands because they're very close by. We've done quite a bit of research with them. And yeah, so really we work in all fields that could possibly use STEM.
That is very cool. They're asking me for the secret code word, and in case you didn't see it, today's secret code word is going to be shockwave. So shockwave is your secret code word. And I did put up the screen to show you where to go to look at the rest of the events for today. And then we have events all day tomorrow that you can just stream live on our website. You don't have to sign up for or anything. And if you guys submit a feedback form at that bit.ly link right there, Feedback Sci-Fi, every day we're giving away a prize. So you can submit those online on our website. You can find the link. And I want to thank everyone for coming. I want to thank everyone from New Mexico Tech sharing us these I'm sorry, it's Friday. Sharing these experiments with us. And we appreciate everyone watching. Were there any more questions? Jasmine, are you raising your hand for a question? Or you just have your hand up?
My class would like to say
thank you.
Thank you.
You're welcome, guys.
How would you get the prizes if you won?
Oh,
You guys like.
I can barely hear her. Jasmine, were you asking about how you get the prize if you win from the feedback form?
Yeah.
Okay, your email is collected when you enter the form, and we will email you and let you know if you won. And then we'll either mail it to you or you can come pick it up at Explora. Okay. More questions? Nope, it looks like we're good. So thank you again, and we'll see you all later.
Thank you. Bye-bye.
Bye-bye. Thank you.